So let's talk quickly about Ampere's law. And the way Ampere's law works is very similar to Gauss's law. In fact, it looks similar. We have the integral of the magnetic field around a closed loop along a outer part of a surface is equal to mu naught times I enclosed. So once again, like Gauss's law, the left-hand side is going to be for the surface or the loop, and the right-hand side is going to be entirely about the current. Gauss's law, we had something similar, except the left-hand side was the Gaussian surface, right-hand side was the charge. So one of the typical cases you see for Ampere's law is a coaxial cable, where you have a solid core, a solid wire, and maybe you have some current flowing down, going in the right-hand direction, and then you have this wire actually enclosed inside of a wire shell. And that wire shell maybe has some current going in the opposite direction. So maybe the current in there is also I, but it's going to the left. So in between these two wires, you have just a bunch of empty space. So nothing in between the wires. And if we want to do Ampere's law on this, we can actually kind of rotate this around to give it a slightly different view, maybe make it a little bit more clear. So let's make some space so that we can do that and redraw this picture just a little bit. So we're going to redraw kind of looking down this wire so that we see the inner core, which has maybe a radius of R1. We have the outer shell, which has an inner radius for the outer shell of R2 and an outer radius for that outer shell equal to R3. And we'll just draw a very quick little diagram down here so that we keep in mind what it looks like from the side. Okay. Current going one direction and current going the opposite direction in each of the two portions of the wire. So what I want to do is Ampere's law, mu integral of B dot ds is equal to mu naught times the charge or current enclosed within your surface. So the left-hand side is all about amps surface, right-hand side is all about the current. And we want to find this at various different locations. Let's say we want to find it if the radius of my Amperian surface is less than R1. So that's going to mean that I'm going to be within this inner wire. So I may be an R equal to R that's less than R1. So my Amperian surface, again, I've drawn a circle here to actually enclose my surface. So this circle means that I want the surface to be a circle. If I go around the outer part of the circle, the circular surface, I get B times 2 pi r, because this is the circumference of a circle. And that's going to be equal to mu naught times I enclosed. And the I enclosed within this is going to be the total I. Remember, I have this I that's running through this wire, but I'm not enclosing the total wire. So much like we did with Gauss's law, I have to kind of scale that. So my total current I enclosed has got to be equal to I times my Amperian surface. It would be pi r squared, surface area of that Amperian surface. And I need to scale it by the total surface, pi times r1 squared. So then my answer to part A, where r is less than r1, is going to be equal to B times 2 pi r equals mu naught times I times pi r squared divided by pi times r1 squared. And you can do some algebra to get out the final answer. Just do your simple algebra to find that B is equal to mu naught times I times r over 2 times pi times r1 squared. And that's going to be your magnetic field for r is less than r1. Now we can move onwards, and we can move to a slightly different part. So let's get rid of all this other stuff. You have to bear with me. I'm using a slightly new program. Had a iPad failure. Part B is going to be nice and easy. Part B, we want to find in part B, we want to find what is the magnetic field if R is between R1 and R2. So instead of being in this inner part, you can get rid of that. I am now in between. So my Amperian surface is somewhere in between R1 and R2. So now I have, that's my R. So again, my surface is a circle, so I get B times 2 pi R, because I'm going around the circumference of a circle, equals mu naught times I enclosed. I enclosed here is going to be whatever current I have going through this inner wire. I don't need to worry about anything going on in the outer part, because this outer part is outside of this Amperian surface that I've drawn. All I care about is everything that's inside of this. And how much current is inside of there? I have a total current of I, which we remember from our very initial picture. So, this part, nice and easy, B equals mu naught times the total current, because that's the current that's enclosed, over 2 times pi times R. And part B is done. Get rid of part B. Again, with Amperes Law questions, the challenging part is really going to be figuring out what is that current, what is I that's going on for each of these. Okay. Let's clean up our picture a little bit. Redraw some of these things. We have this inner surface that's got R1. We have this inner part of the outer shell that has a radius of R2. And now for this part, I want to know what's going on if my R is greater than R1, or greater than R2 rather, and less than R3. So that's going to put me in between, in the middle of this inner shell, or this outer shell. So I want to know what's going on inside of the outer shell of that coaxial cable. Once again, the left-hand side is my Amperian surface. That's going to be B, just B times 2 pi R. The hard part is now going to be figuring out what's mu naught times I enclosed. Now right away, I know that there's two parts of the current. If I look down here at this bottom picture, I can see I do have an entire current of I that's going to the right. But then inside of that shell part that I'm in now, I have some current that's actually going to the left. So I need to account for both of those. So the I that's enclosed here has to be equal to the total current I that's going to the right due to this inner core wire, and I have to subtract off the contribution of the current that's going to the right, or to the left, from the shell of this wire. But I'm not enclosing that whole shell. I'm only enclosing this little shaded part in here. So I have to scale that. I have to scale my total current the same way I did in the first part. So to scale that, I need to take the surface area of my Amperian surface, which is going to be equal to pi times r squared, which is the outermost radius of my Amperian loop. But I need to subtract off all of the space between the middle and this inner radius of my shell. So I need to subtract off pi times r2 squared. But I need to scale this by the total size of this shell. So the total size of this shell, this outer shell, has to be equal to the outer radius way out here, minus the inner radius portion. So I have my pi times my r3 squared minus my pi times my r2 squared. And now I can find that my magnetic field is equal to mu naught over 2 pi r times my current that's enclosed, which is going to be I minus I times pi r squared minus pi r2 squared, all divided by pi times r3 squared minus pi times r2 squared. And that will be my final answer for inside of the outer part of the coaxial cable. And then part D, we're going to do very, very quickly over here on the end. Part D, I have R is greater than R3. So that means that I'm outside of all of this, outside of the whole wire. Once again, on the left-hand side, I'm going to get B times 2 pi R. And if I look at this, and actually I'm going to look down at this bottom picture, what's the total current that's enclosed if I'm outside of all of this? Well, I have a current I that's going to the right, and I have a current of I that's going to the left. So I'm going to get I minus I, and they're going to cancel out to give me zero current. So I have zero current that's enclosed. That means I'm going to get a zero on the right-hand side. So that means that the magnetic field, if I'm outside of this coaxial cable, is equal to zero. And it's very useful for designing a TV, coaxial cable in a TV. That way you don't create magnetic fields to interrupt with things or to attract itself to maybe metal inside of your wall or metal inside of your TV. So that's how we do Ampere's law in a coaxial cable.